Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So welcome to part 2 of our video on the two-way block ANOVA, also known as the two-way ANOVA without replication, or the two-factor ANOVA without replication. Now hopefully you have watched part 1, so you have a good conceptual background of what the two-way ANOVA actually is. So when we do the actual calculation in part 2, you'll know exactly where it comes from. So we're going to do a little bit of PowerPoint first, just a couple of slides. Then we're going to actually go into Microsoft Excel, do the two-way ANOVA calculation by hand. We'll compare our answer to Excel's built-in formula and output generated from SPSS. Once we look at all that, they should all match. Let's go ahead and get started on part 2 of our video on the two-way block ANOVA. Now, if you have not gone and downloaded the file that we're going to use in this, please check the description below the video here on YouTube. You will find a link to the corresponding blog post for this video. There, you can download the Excel file, and then of course you can open it up and follow right along with us as we go forward. So I really encourage you to do that before going any further. Let's go ahead and get started. So we're going to look at this as sort of a challenge. We're going to go into Excel and do the calculation actually by hand, and hopefully our result matches what a dedicated statistical software package like SPSS would give us if we did it in SPSS. So here is the output from SPSS, and you can see that we have all kinds of sum of squares, degrees of freedoms, and mean squares, and F ratios, and significance, and everything else. Now, some of that is not going to be applicable to us, namely the intercept line there on the top of that table. We'll forget about that for our purposes. But the city and the shopper rows are of high importance to us. That's actually the meat of this problem. So remember, we are interested in the differences between the cities. So we're looking at the scores, the secret shopper scores between Sydney, Brisbane, and Melbourne in Australia. So we want to know if a difference exists somewhere between those three cities. But we want to sort of account for or block out any variation in the shoppers themselves, so we can get a clearer picture of what's going on with the cities. We want to find the differences in the cities while blocking out or removing shopper differences from the error term. And again, in part 1, I explained this in great depth, so I'm not going to do it again here. But we're really trying to minimize the error term by assigning some of the error to the blocks or the shoppers. And that'll give us a clearer picture of the city differences. Now, I do want to point out, sort of as a side note here, is that we could turn this problem sort of 180 degrees. We could test for secret shopper differences while removing city variance from the error term. So it's sort of a transposed or flipped way of looking at this same problem. But for this problem, we're not interested in that. We're interested not in the shoppers. So if I work for Starbucks, I'm not really interested in the shoppers. I am interested in the mean scores for the cities. So I want to know if Sydney is doing better or worse than Melbourne, if Melbourne is doing worse or better than Sydney and Brisbane, etc. I'm interested in the cities. But you could flip this on its side and look at differences in the shoppers as well. It works both ways. Just sort of a side note. Okay, so let's look at some basic formulas that we're going to be working with in this two-way block ANOVA. And some of these are very similar to the one-way ANOVA. So we have N equals total observations, and C is the number of columns or groups or treatments, in this case, cities, which are 3. And of course, N in this case is the total number of observations, which is 6 shoppers times 3 cities, which is 18. So SSC is our sum of squares columns. So we can think of it as treatments, depending on the problem, columns, groups. Again, in this case, it's cities. Now, the degrees of freedom for the columns is C minus 1. So the number of columns we have minus 1. And then when we find the mean square columns, that's going to be the SSC divided by its degrees of freedom. So when we calculate the SSC in Excel, again, we'll divide that by the degrees of freedom, which in this case is 3 minus 1, which is 2. Now the SSE is the sum of squares error. Now for this two-way block ANOVA, the degrees of freedom for the SSE is C minus 1, which is the number of columns minus 1, times the number of blocks minus 1. And the MSE will be the SSC divided by that degrees of freedom. So you can see the pattern here. The degrees of freedom is dependent on whether we're doing with columns or blocks. And of course, the error, it deals with both. But the mean square columns, or mean square error, is the sum of squares divided by its degrees of freedom. So the total SST, the total sum of squares, degrees of freedom is N minus 1. So in this case, that would be 18 minus 1, which is 17. And then we're going to have this F ratio, which is mean square columns divided by the mean square error. Now, you notice we're missing something here in this chart, and that's sort of what's new in the two-way ANOVA, and that is the blocks, or the rows. So B is the number of blocks. So SSB is sum of squares of the blocks, or the rows. Now the degrees of freedom for the blocks is just the number of blocks we have minus 1. In this case, 6 minus 1 will be 5. And the same pattern applies here. So the mean square, that should be MSB equals SSB divided by the degrees of freedom for the blocks. Same idea. SSC, sum of squares of the columns. So degrees of freedom are 3 minus 1. That's C minus 1, which is 2. So in the end, we'll have SSC divided by 2. That'll be our mean square columns. For SSE, again, remember that's 2 times 5, because 2 is our degrees of freedom for columns, and then 5 would be our degrees of freedom for blocks here in a second. So 2 times 5 is 10. So MSC, the mean square error, is SSC divided by 10. Total sum of squares, again, N minus 1, so 17. Everything else is the same. Now for the blocks, it's just 6 minus 1 because we have 6 blocks. So the MSB, again, sorry about that, will be SSB divided by 5. So 6 minus 1. Okay? So that's where we get all of our basic numbers from. So now let's actually go into Excel and actually do a calculation sort of by, quote, hand. We're not doing it on like pencil and paper, but we're going to do it in Excel using formulas, and then we'll paste everything and see if we can generate through our own work, through our own arithmetic, the same output that both Excel's built-in ANOVA formula give us and SPSS's output gave us. Let's go into Excel and do that. Okay, so here we are in Excel 2010, and I assume that if you're watching this, you have gone to the corresponding blog post, which you can find in the video description on YouTube, have downloaded the file, have opened it up, and are now following along with me step by step. If you have not done so, I encourage you to pause the video, do that, and then pick it up once you've opened up the file. Now, as you can see, we have a lot of things going on in this Excel spreadsheet. So I'm going to walk you around and sort of show you where everything is at before we dive in. Now, the first thing I want to draw your attention to are the tabs in this workbook on the lower left. So you'll see that we have 5 tabs. We have a Data tab, and then we have an SST tab, then we have a red SSC tab, then we have an SSB tab, there it's blue, and then finally we have a relatively blank Excel tab, and that is where Excel's own output, when we check our work against Excel's to make sure it's right, that's where this will go. So let's go back to the Data tab first. So let's walk around this first tab, and let me sort of point out what everything is. Now, up in the top left, we have our original data, which is actually from part 1 of this video. So you can see that we have the 3 cities, so Sydney, Brisbane, and Melbourne. And on the left-hand side, we have our 6 secret shoppers. And of course, we have our 18 ratings that comprise our data points. So we'll get to that here in a minute. Now, in the upper middle, we have some basic information about our data. So we have 18 groups, we have 18 data points, so n equals 18. We have 3 groups, so C is our columns, that equals 3. And then blocks, B, we have 6. So we have a total of 18 data points, 3 groups, which is the 3 cities, and then the 6 blocks, which are the 6 secret shoppers. Now on the upper right, we actually have a slide from part 1 of this video, just to remind ourselves what we're actually doing in this exercise. So we're taking our overall sum of squares in the problem, and we are dividing it up, or partitioning it, among 3 sources. Either the columns, so SSC, the blocks, SSB, or whatever's left, which is error, SSE. And ideally, we would like the error to be as small as possible and have most of the sum of squares be attributed to the columns and the blocks. Now on the bottom right, this is the actual SPSS output when I did this problem in SPSS. So hopefully, once we get our numbers over there on the left, we can check it against that to make sure they are right. So really, in the end, we're going to have the correct answer, hopefully, in 3 places. We're going to have our own hand calculation, we're going to have Excel's output, and we're going to have the SPSS output we have here on the lower right. Now there in the bottom middle, we have 2 very important ratios. So those are our 2 F ratios. So if we do this correctly, those 2 F ratios should match the 2 ratios in the SPSS output over here on the right. So those 2 should match when we're done. Now over here on the left is probably our most important table in this Excel spreadsheet. So this is kind of where we're keeping track of everything that's really important as far as our calculations go. So in the blocks across the top, we have SST there in the green. That's our sum squares of total. Then we have SSC, SSB, and SSE. Now below each one of those, we have their corresponding degrees of freedom. So degrees of freedom for SST is n-1. For SSC, it's c-1. For SSB, it's b-1. And for SSE, it's c-1 times b-1. And then below that, we're going to have our mean squared components. So it's just the sum of squares divided by the degrees of freedom for each one of those sources of variance. So this is sort of like the control panel of what we're going to be working with. Now let's go ahead and go to the SST tab here in the lower left. So here you can see we're going to hand calculate the sum squares total by looking at each individual data point and the overall mean. So we'll do that here in a couple minutes. If we go to the SSC tab, we're going to do the same thing, but for the columns. If we go to the SSB tab, again, same thing, sum squares for the blocks. And then the Excel, again, is relatively blank, because this is where Excel's own ANOVA output will go. So let's go back to the Data tab, the first tab. Now we want to take care of a few things here that will get us started. Now, the first thing I want to do is calculate the row and column means and the overall mean for our data. Now, I forgot to mention that I am going to assume you have some basic Excel knowledge. I'm not going to go into a whole lot of Excel theory. We're going to be using some very simple formulas like average and sum, and we're going to square a few things and stuff like that. So it's not all that complicated, but hopefully you have some basic Excel experience before doing this. So the first thing we want to do here in cell E2 is find the average, or the mean, of all of shopper 1's scores. So we can do that easily by using equals average, and Excel will predict what you want. So average, and I want those 3 scores. So close parentheses, hit enter. So we can see that shopper 1 had an average score of 80 across all 3 cities. Now I'm going to do the same for shopper 2. Now, if you used Excel, you know that you could just drag down that top formula. The problem is it also changes the colors. So I got to do this manually for each one. So all we're doing is calculating the average for each shopper. So hopefully you're following along with me. All right, one more. Okay, there we go. So we can see that shopper 1 had a mean score of 80, shopper 2 70, 60, 70, 75, and 65. So now we need to do the same thing for the cities. So we'll do Sydney first, so average for Sydney, average for Brisbane, and the average for Melbourne. There we go. So Sydney had an average or a mean of 67.5, Brisbane 65, and Melbourne 77.5. Now we need the overall mean. So the overall mean for all 18 data points. Now, there are 3 ways you can do this. We can find the average of the columns, of the column means there. So the row means 70. Delete that. We could do the average of the column means. So across there, 70. Or we could do the average of everything. So average and select all 18. Again, that's sort of the point of this sort of cross-tab looking ANOVA. Okay, so we have our row or block means, we have our group or column means, and we have our overall mean of 70. And the next thing we can do while we're here are the degrees of freedom for each one of our components. Let's go down here to the SST degrees of freedom. That's n minus 1. So we know n is 18 because we have 18 data points, so n minus 1 is 17. So for the columns, the degrees of freedom is c minus 1, so c is 3, minus 1 is 2. For the blocks, it's just b minus 1, which is 6 minus 1, which is 5. And the error is c minus 1 times b minus 1. Well, that's 2 times 5, so that is 10. And notice that 2 plus 5 plus 10 is 17, and our total degrees of freedom on the left is 17. So let's go ahead and center these, just like that. Okay, so I think that's about all we can do for now here on this first tab. But that gives us a good start. When we come back to this, we'll sort of put in the other figures and fill it out as we go. Okay, so let's do our first calculation here, and that'll be the SST. So let's go to the SST tab, the green tab, and here we are. Now, what I've done here on the right is I've sort of paired out each shopper and each city. So we have shopper 1 Sydney, shopper 1 Brisbane, shopper 1 Melbourne, and then the same thing for shopper 2, 3, 4, 5, and 6. So it's each shopper and city pair, and then the rating that goes with that pair. Then the next column is our overall mean. So remember, when we're doing the SST, or any of these sum of squares for that matter, it's just some figure, in this case it's the individual data points, minus the overall mean. That'll give us a difference. And then we square that difference, and then we add up the differences. That's why it's called sum of squares. This we can do the fast way. So we need the difference between the rating and the overall mean. So equals, then we'll select the rating cell, minus the next to it, the difference, the overall mean, and hit enter. So 75 minus 70 is 5. Now we can hover over the lower right corner of this cell. It'll turn to the solid black sort of cross, and we can drag down, and that'll fill down the whole 2 columns for us. Okay, so let's go ahead and square all those. So equals, then we'll select the difference, shift 6, which is a little caret, we'll squared, so put a 2, and we square that. So 5 squared is 25. Now we'll do the same and drag down to fill that in, and there we go, easy enough. Now we need the sum of all those square differences. So equals sum, and we'll select all 18 of those and hit enter. So 1750. So if we go back over here to the left, where it says SST, we'll say 1750. Now let's go back to the first tab for data, and under SST we'll put 1750. I'm going to center that. Actually, I'm going to go ahead and center all these, as I know we're going to need them. There we go. So SST 1750. Now let's figure out the SSC, or the columns. So let's go to the red tab for SSC. Same thing. So the difference, so equals the column mean for Sydney minus the overall mean. Enter. Then we'll drag down to get all 3 of those. Now we're going to square them. So equals the difference. Shift 6 for the caret, squared. And there's our squared differences. Now we sum those up. So 87.5. Now look over here on the left. To find the true column sum of squares, it's just not the sum of those differences. What we have to do is multiply that by the number of shoppers we have. So we take the squared differences in the columns, so our 3 cities, and then we multiply it by the number of shoppers we have. So in this case, it's 6. So if you look down here, we have SS times B. So B is the number of blocks, which is 6. So SS, sum of squares, times 6. And then when we do that, we end up with 525. So 87.5, which is our sum of squares over here on the right, times 6, which is the number of blocks we have, is 525. So let's go back to our first tab, and where we have SSC, we'll do 525. Now we'll note, if you look over here on the SPSS output, you'll see that for city, that's our columns, you'll see that the hypothesis sum of squares is 525. So that's a good sign. That means we're doing it right. So let's go to the SSB tab now. Now we're doing the sum of squares for the blocks. Same process to the difference. So row mean minus overall mean. Drag down to get all of those. Now we're going to square them. Squared. Drag down to fill. Now we'll sum them up. Equals sum. Those 6 square differences. That's 250. Now, if we go over here on the left, we'll see that now, to find our block sum of squares, the true block sum of squares, it's our sum of squares times C, which is the number of groups, or columns. So it's 250 times 3 for the 3 cities. You can think it's the opposite. So when you find the difference for the rows, you multiply that by the number of columns. When you find the difference for the columns, you multiply that by the number of rows. It's just that simple. So this is 750. Let's go back to our Data tab under SSB, and it's 750. Now, how do we find the error? How do we do that? Well, remember that they have to add up. So the SSC plus the SSB plus the SSE has to add up to 1750. So we can find this by simple subtraction. So SSE equals, or SST minus the SSC minus the SSB. And that is 475. Now look over here on the right. What do you notice for error? Error 475 for shopper. Error 475. Ignore this enter step for now. Don't even pay attention to that. So the error is 475, which matches our sum of squares error. Now the next thing we have to do is actually find our mean squares. So we have to divide each one of these by its degrees of freedom. So MST is mean square total, MSC is mean square columns, MSB is mean square blocks, and then MSE is mean square error. So it's just simple division of the sum of squares divided by the degrees of freedom. So for MST, it is equals 1750 divided by 17. So 102.94, etc., etc. Now for SSC equals, by the way, that one doesn't really matter that much, but we'll do it. So SSC, this one does matter, 525 divided by 2, 262.5. Now we go to SSB equals 750 divided by 5. It's 150. Now for the MSE equals 475 divided by this 10 here. Okay, so those are our mean square sum of squares, or our means. Again, that's just divided by the degrees of freedom. So let's check this out. So MSC, if we go over here to our SPSS output, we go to mean square city 262.5 right here. If we go to MSB, again, which is the shoppers, so mean square for shopper is 150, same thing we have. And the MSC, or the error term, it's 47.5, so we did it right. So we are good. So all this looks fantastic. Now we defined our F ratios for all this. So the one we're interested in is this MSC divided by the MSE. Again, that's our mean square columns, or our groups, our cities, that's what we're interested in, divided by the error. So it's a ratio of the mean square columns to the error. Because remember this chart up here in the upper right. We're comparing the columns to the error, and we're comparing the blocks to the error. And we want the error to be as small as possible. Now if you look at the mean square columns, mean square blocks, and mean square error down here in the lower left, you can see that the mean square error is smaller than both of those two, which is good. That's good. So let's go ahead and do this division or ratio, however you want to think of it. So MSC divided by MSE. So this is equals MSC, which is down here in the lower left, divided by MSE, which is right next to it, and that is 5.526. So let's go ahead and do the same thing for the blocks. So equals 150 divided by 47.5 with the MSE. Hit enter. That's 3.158. Now, look at our SPSS output. What is our F ratio for city? 5.526. Excellent. Good work. How about shopper? 3.158. So is ours. Excellent. So guess what? You have just hand calculated a two-way ANOVA without replication, or a two-way ANOVA block, randomized block, by hand here in Excel. And again, we did it this way so you can actually see where the numbers come from. Not just a bunch of formulas you smash into your head and you try to work around and just say, okay, the answer is right, but you don't know where it comes from. So all we did in this Excel example is show you where the stuff actually comes from and how you could actually do it by hand. If you needed to, look at how we're taking this overall sum of squares and trying to attribute it or place it or partition it between the columns, the blocks, and the error. And again, hopefully in the end, the error, the MSC, is much smaller than the MSC and the MSB. Because if that is the case, then that means the columns and the blocks sort of eat up all of the variance, and that means that there are differences there. You know, as researchers, we're not looking for or hoping for any differences, but a smaller error allows us to pick up or detect differences in the columns or the blocks much, much easier. Okay? Now, I have one last step, just to sort of show you how Excel does this. So we're going to use Excel's built-in Two-Way ANOVA without replication tool, just so we can learn another way of doing these type of problems. Now, you do have to have your data formatted how we do here, okay? And actually, I'm going to go ahead and just type shopper, not shooper, up here in the top, so Excel likes that better. Okay, so we're going to go ahead and do the Two-Way ANOVA in Excel itself. We go up here to the ribbon, we'll select Data, and then over here on the far right, we will see Data Analysis. So we'll click on that. So here we have our Data Analysis tool. Now we're doing ANOVA two-factor without replication. And again, that's another name you might hear for this. So two-factor. So in this case, we have the city factor, and then we have the shopper factor, two-factor. Now without replication, that's because we only have one data point in each cell. We'll get to with replication later. So we're doing two-factor without replication. Go ahead and click OK. So once our input range, so I'll just select this little button over here next to it, and then I will select everything, including the column headings and the row headings. Going back to this, I'll check labels. That tells it that it does have headings. The alpha is 0.05. We'll stick with that. That's pretty standard. And the output range, I want to determine that it will go in Excel tab up here at the top. Click on that. So we are good to go. Click OK. And there it is. So we'll expand these out a bit so we can see everything. Anybody else out there as neurotic about that as me? Okay, so let's compare this with what SPSS gave us. So we'll drag this over here. Okay, so first thing, we'll look at our sum of squares. So remember we had 750, 525, I'm sorry, and 475. That's the same thing we did by hand. Same thing. Degrees of freedom, again, we did that by hand. Same thing. Mean square, we found that. Now let's compare our F ratios. So for our rows, remember that is our shoppers. Our F ratio is 3.158. Look at our SPSS output, 3.158. Good. Now we'll go down to our F ratio for columns. So 5.53, 5.526. Go to our SPSS output and it's 5.526. Excellent. Okay. Now this gives us p-value, same thing, and our F crit. Now let's talk about actual hypothesis here. So remember that our alpha was 0.05. So if we notice that, so we'll notice that the city significance value is 0.024. So is that significant? Yes, it is. So we can say that a p-value of 0.05, that a city difference does exist, or is likely to exist. So 0.024. Now the shopper is not significant, but barely, 0.057. That's pretty close, but it does not meet the 0.05 threshold. So what can we say here? It does seem to indicate that the city scores do have legitimate differences, even when accounting for variation in shopper scores. Because remember, that's what we're sort of doing here. We're trying to account for the variation in the shoppers, take that out of the error term, and then compare what's left of the error to the city scores. So we're not really controlling for shopper in the statistical sense, but we are accounting for some of the error variation by subtracting out what's in the shopper from it. This is good. So there is some difference in the city scores, even accounting for the variation in the shopper. Let's go back to tab 1. We can see that everything here is correct and fits nicely. So now you know where the calculations come from for a two-way ANOVA without replication. You know how to do it if you ever had to do one by hand for some odd reason. But more importantly, you know where the numbers actually come from, what they're actually doing, what they represent in the overall scheme of the two-way ANOVA. Let's go back into PowerPoint and finish this up. So we are back from Excel. Let's go ahead and summarize some of what we found. So our SSC was 262.5, our SSB was 150, and our SSE was 47.5. Sum of squares total, again, was 17. Now remember, the F ratio we were interested in had to deal with the columns. We have mean square columns of 262.5 divided by the mean square error, or the MSE, which was 47.5. So that gave us an F ratio. Again, remember, an F ratio is a ratio of two variances. We talked about that in the F ratio videos a while ago. So the F ratio is 5.53. We have mean square columns divided by mean square error. And that gives us this sort of nasty looking thing. But all this says is the F ratio at whatever alpha level, degrees of freedom columns, degrees of freedom error. That's what the C and the E mean. That's all that is. So F of 0.05, comma 2, comma 10. That tells us all of our degrees of freedom when we look the ratio up in the F table. Now we could also do that in Excel using the F inverse right tail formula. So f.inv.rt, and then in parentheses we actually put the numbers that we have down below. So 0.05 is our alpha, 2 is the degrees of freedom in the numerator, or MSC, and 10 is the degrees of freedom in the denominator, or the MSE. Now when we do that, we come up with an F critical value of 4.10. That's what it gives us back. What we ask ourselves is our F statistic in our problem of 5.53 larger than the F critical we found in our F table. And again, remember, the F table, you need three things. You need the alpha level you're working with, you got to have the numerator degrees of freedom, and the denominator degrees of freedom. That's how an F ratio works. So the F crit was 4.10. Now our F stat for cities was 5.53. So what can we do with the hypothesis? We can reject the null hypothesis. So significant differences in mean quality score was present by city, okay? Because remember, our null was that there was no difference. So the null always assumes that there is sort of no difference. And in this case, we had to reject that null because our F statistic was larger than our F critical. So significant differences in mean quality score do exist by city. But again, the question is, or the extension to this problem is, well, where? So here is a chart that is generated by SPSS. Now what we have on the bottom are the 6 shoppers. So shopper 1, shopper 2, shopper 3, etc. Actually, we have shopper 6. And then on the vertical axis, we have the estimated marginal means. So that is the mean for each city by each shopper. So what do you notice here? Now again, I made this data up on purpose so it would look like this. Now what we can see is that they tend to follow a parallel. So shopper 1, shopper 2, and shopper 3 were consistent with each other. Okay, as you can see that they're basically parallel as you go across. And consistently, Melbourne was the highest, Sydney was the middle, and Brisbane was the lowest. Now you'll also notice that Melbourne was significantly higher than the other 2 cities by all 6 shoppers. And again, I did this data like this on purpose so it would look like it. So it would appear that Melbourne is sort of the one that's different than the other two because it's so far away, and that is the one that is different. Now, I'm not going to go into anything post hoc tests like the Tukey and so forth. I'll say that maybe for another video, or I may not do a video on those altogether. But again, a simple chart like this can sort of show you visually where the differences actually are. Okay, so let's wrap this up. So why ANOVA in the first place? So remember, up to this point, before we started ANOVA, we were only comparing two populations with the independent samples t-test, which is a random one, and then match sample, which is paired. But of course, limiting ourselves to the comparison of two populations is, of course, limiting. The world is much more complex than just two populations. So what if we wanted to compare the means of more than two populations? What if we wish to compare populations each containing several levels or subgroups, like in this problem? So that's why we use ANOVA, or the analysis of variance. Now in this problem we had the blocking variable. So what exactly is the purpose of a blocking variable? So remember, ANOVA is about teasing apart or partitioning the total or overall variance into different parts. So assigning parts of the overall variance to different sources. Now one of those parts is always error. It's the unexplained source of variance, and it will always be there. Now in a one-way ANOVA, aside from error, we were only working with one potential source of variance, and that was the columns or the groups, because there were no row differences. Each column was just a random sample of whatever we were looking at. Now in a two-way ANOVA, we introduce a new way to separate out that data, and that is blocking, or the blocks. So the blocks allow us to further refine how we assign or split apart the overall variance, allowing for more powerful hypothesis tests. So we're always looking to reduce the error term by assigning it either to the columns or to the blocks. So if we're interested in column differences or group differences, if we can assign some of the remaining error to the blocks, then we are able to find differences in the columns much easier. And that is the overall point of the blocking variable.